Thank you for joining us. I'm Eleanor, and it's my honor to welcome you on behalf of SeaNovation. At SeaNovation, we believe some of the world's toughest challenges, from food security to water management, can be solved where science, entrepreneurship, and industry meet. Based in Eilat and Eilot, at Israel's southern tip, we work with startups, researchers, and corporates to turn big challenges into opportunities. We're very fortunate to be supported by an incredible ecosystem, which includes the Israeli Innovation Authority, the Ministry of Economics, the Ministry of Agriculture and Food Security, the Ministry of the Development of the Negev and Galilee, the Ministry of the Regional Cooperation, the Eilat Municipality, and the Hevel Eilot Regional Council. We are also proud to partner with the AquaculTech site, the National Center for Mariculture, our Dome, the Israeli Innovation Institute, the Israel Ports Company, and the Ben Gurion University. I would like to show you a clip, a 1-minute clip that summarizes what we're all about here.
Welcome to Eilat, Israel's southern frontier, where desert meets sea and innovation meets opportunity. Here, at the heart of the Red Sea, unique ecosystems remind us how fragile and how resilient our world can be. Protecting and sustaining them requires bold new ideas. That's why we built SeaNovation, an innovation center chosen by the Israel Innovation Authority to support startups from idea to impact. We connect entrepreneurs with mentors, grants, and real-world infrastructure to test and scale their solutions. From labs and aquaculture pools to cutting-edge marine research, SeaNovation is shaping the future of food, water, and sustainability. Jump into the deep end of innovation with us and be part of the ecosystem.
So while today we'll hear from leading experts in regulation, water management, and research, we also see this as a call to action. If you're a startup, a researcher, or an entrepreneur with a fresh perspective, we want you to know there's a place for your ideas here. I would like to take this opportunity as our esteemed guests of our webinar to invite you to our demo day, which will be on September 8th, where you'll have a first look at the ventures graduating our 6-month accelerator and meet us personally to learn more of the opportunities SeaNovation offers. Right now, I'll pass the baton to our esteemed moderator, Ronnie Sussman, CEO of AquaculTech, who is a leading expert of aquaculture, and it's an honor to have her here today to lead this webinar.
Thank you very much, Eleanor, and thank you, SeaNovation team, for cooperating with this to hold this webinar. And hello, everyone. Our focus today is on effluent management and challenges, a critical issue in the aquaculture sector, very important for sustainability and food security and environmental protection. Our first speaker is Dr. Uri Yogev, an aquaculture and water treatment specialist and researcher who will provide us with a comprehensive introduction to effluent. What is it, why does it matter, and how it impacts our aquaculture ecosystems. Thank you, Uri. The stage is yours.
Okay, thank you. So I will talk about effluent in aquaculture. And when I'm talking about aquaculture, so we can see here in the graph, it's the production of fish and seafood during the last 70 years. Blue is fishing, it's capture, and red is aquaculture. And we see that since the 90s, aquaculture, capture fishing is more or less stagnant, and all the gap between the demand to the production is filled by aquaculture, which is now is the fastest growing sector for food production. it's provide more of the 50% of the fish we are eating today. It's about 160 billion annual industry, and its industry it consists mainly from small-scale farm. About 80% of the industry is small-scale farm, not like we familiar in Israel. And when we grow fish, we give them rich protein feed. About between 30 to 60% of the feed is protein. It contains about 1 to 2% of phosphorus, about 8% nitrogen, and the rest is mainly carbon and oxygen. And fish are very, very efficient in converting feed into biomass. They eat most of the feed, and about 20 to 30% of the feed is converted as biomass, and all the rest is excrete. Most of them, more or less, half is excreted as feces, as suspended solid, and half as a dissolved. And the nitrogen is very interesting because they excrete the nitrogen as mainly as ammonia, which is very, very toxic to the fish. And when we grow fish, this is one of the main limitations. We need to somehow remove the ammonia to a non-toxic level. And we can see here in a graph that we can see the water we need per kilogram of feed and the nitrogen, the ammonium nitrogen concentration in the water. And we usually target for 1 to 2 milligram per liter, which is considered a non-toxic concentration for fish. And as you can see, we need about 10 to 15 cubic meter of water per 1 kilogram of fish, of feed we supply to the fish. And that's sorry, and that's one of the way we produce fish. And when we're talking about inland, so there are two main technology to produce fish. First is flow through. Basically, it's tank of water that we put new water and flow through the tanks and discharge, usually very high flow, and basically there are no treatment. Dilution is the solution. And it's very similar to sea cage and all the rest of the technology that there is no treatment. And the second one is recirculating aquaculture system, or RAS. When we have several treatment units that treat the water, that enable reuse of the groundwater for growing fish. Basically, there are two main units. First is the solid removal to remove the suspended solid and producing a second stream of sludge. And the second one is nitrification that convert the toxic ammonia into less toxic nitrate, which is about 2 orders of magnitude less toxic, enable reduce the amount of water. And if we look at the same graph, so basically what we are doing, we're converting the ammonium nitrogen into nitrate and enable to reduce the water need to about 100 liters of water per 1 kilogram of feed. And these two systems we can see that the flow are different, but the concentration is the opposite way. When we use high flow, we have diluted the contaminants, and when we use the recirculating, so the concentration is much higher, which is that affecting the way we treat the water and different challenges. And if we want to define what is the effluent, so basically it's all the water stream that released from the farm. It can carry many substances, and we see them soon. So when mainly chemical and biological, when we talk about chemical effluent, so we can say there are four groups. First is the suspended solid, the feces, and the undiluted feed, and usually some biofilm and biofloc that produce in the system. Second is the nutrient, nitrogen, phosphorus, and metal that mainly come from fish excretion. Organic matter, dissolved organic matter, mainly again fish excretion and microbial activity. And the other one is micropollutant in some system, some medicine and veterinary drugs, and some hormone that usually produce when we talk about production of hatcheries and brood stocks, not for grow up. The second type is biological effluent, microorganisms that can proliferate in the system, and parasites that when we go in high density, can occur in the water. And again, another type is genetic material, like like eggs, sperm, and all kind of genetic material that fish or seafood produce. We can say that there is three environmental impact or challenges. First is the short one, that changing the water quality where we in the receiving party. Second is much longer. It's ecosystem change, mainly to changes in microbial community or pathogen. And third one is the long-term concern. And therefore there is some treatment is needed. And today the basic treatment have four stages. First is solid removal, then nutrient removal, mainly related to RAS system, because in flow through it's very, very challenging to do that. Then polishing, and then disinfection. Now the regulations say in Israel for seawater, for sea discharge, for UV radiation, it's about 212 millijoule per square centimeter, and chlorine about 0.1 milligram per liter after 60 or 50 minutes. And the future will be, as I believe, that we will change from removal into recovery. Now there are three main systems. First is the aquaponic, and biofloc and IMTM. In all of them, we convert all the excess nutrient into a second product that can be sold and reduce the effluent. And that's it. Thank you. I think there is some question in the end, right?
We'll be taking questions at the end. Thank you very much, Uri. I would like to present Dr. Sharon Zmora. Just a second. Sharon is the Desalination and Water Quality Engineer at Mekorot Southern Region, and she will discuss unique challenges desalination brings to our sensitive marine environment. Sharon, please go ahead.
Hi, can you hear me fine? So I'll be talking about the challenges that we have in the Gulf of Eilat. So a few words on, just a second. We are situated in Eilat, which is the very southern tip of Israel, and we are talking about the whole Arava region in terms of water supply. Mekorot is the national water supplier. We're talking about the whole Arava region, which maybe is about 15% of the land area of Israel, but only about approximately 75,000 inhabitants. Just a second. And this whole area has no freshwater sources. I mean, all the water sources that we have in this area is only brackish water. None is drinking water quality. And all the water supplied for drinking in this area is produced by desalination. And we have local desalination plants for small villages around the central and southern Arava, where each village has its own desalination plant. And we have the main desalination plant in Eilat, which supplies water to the city of Eilat and also to agriculture in the whole southern Arava region. And if we're talking about the potentials, we only have about up to 18 million cubic meters of water per year of desalinated water, and also limited in the brackish water that we can supply. All this is from groundwater. So a few words about desalination. Basically, RO desalination, reverse osmosis desalination, is based on membranes and RO membranes, where we put in water feed in one side of the membrane, and by applying pressure, we produce product, which is the fresh water, the potable water, and we have a by-stream of concentrate. And this by-stream is very problematic in general in all desalination plants around the world, and there's always the questions where you dispose this concentrate. And whatever you have in the feed, you will find in the end in the concentrate. the amounts would be the same amounts. The concentration, of course, would be much higher in the concentrate according to the how much product you produce and how much concentrate is left over. So this is our main problem. If we're looking at the Sabra desalination plants, it's actually 3 desalination plants that supply water to all of them, to Eilat and the southern Arava region. And we have 23 or 24 actually source wells, even more. And they are spread from Eilat and up to 25 and even 85 kilometers north. And from there, we have 2 desalination plants, Sabra A and B, which desalinate this brackish water. And this is our main source of water. This produces approximately 15 or 14.7 million cubic meters a year. We also have a small seawater desalination plant, Sabra C, which can produce up to 3.3 million cubic meters per year. And this is all the source of our potable water. Most of it goes to Eilat, and the city of Eilat is growing constantly and is growing and is also seasonally inhabited by very many tourists, by thousands, 10,000 tourists. It almost doubles itself in tourist seasons. And whatever residual we have, we can give to agriculture, and this changes from year to year according to the demands of the city of Eilat. Now, one of our many regulators, we have several regulators, and one of our regulators is the Ministry of Environment. And every runoff to the sea anywhere in Israel is regulated by a committee for the regulation of runoff, of water runoff to the sea, which is headed by the Ministry of Environment. It's a governmental committee, but it's headed by the Ministry of Environment. And this committee limits the amount of nutrients which we may send to the sea with the concentrate. And the Gulf of Eilat is a very sensitive area because it's enclosed and because it has the very rich sea life, the fish and the almogim. Okay, and we are regulated to the limits of nutrients that we may send to the sea with our concentrate. The whole Gulf of Eilat, it was in 2016, it was a specialist committee decided that the limit of nitrogen that may be sent to the sea or added to the sea per year is 22 tons of nitrogen. And we, Mekorot and Sabra, is the major contributor to this nutrient to the sea. So we are limited yearly to 21 tons, which limits actually the amount of water that we can produce. And I'll go into that in a minute. We're also limited to them with the amount of phosphate that we're allowed to send to the sea, to 8 tons per year. We're also regulated hourly and to a limit of concentration, but the main problem is the yearly tonnage. So where do these nutrients come from? So as I said before, we supply the water to Sabra from brackish water wells, from approximately 24 wells, which are extended from Eilat all the way to Savaya, which is 25 kilometers north, and even further north to Faran area, which is 85 kilometers north, and we bring the water all the way to Eilat to be desalinated. Now the water varies in its quality, and it depends on what the local sources are. And some of these wells reside close to agriculture areas. and agriculture areas, and this is throughout the world a problem, and very much a problem also in Israel, not just in Eilat, and even much more in the Mediterranean coast, that wherever you have agriculture, you have agriculture runoff, and you have fertilizer seeping into the groundwater. And this is an example of two wells that we have that are suppliers to Sabra, which are about 200 meters from an area that is irrigated with wastewater and, of course, fertilized. These are palm trees, and we can see over the years that the concentration of nitrate in the groundwater rises. As I say, this is not a local area problem. This is all over the world, and we see it very clearly in the coastal area. And this is a problem. It becomes a problem when you have to remove these nitrates with the concentrate to the sea. So we are limited in the wells that we can use, and we are limited in the amount of water that we can draw from these wells because of this limitation to sea runoff. Another nutrient problem that comes with concentrate is that all desalination has an addition in the process of antiscalants. Now, there are different kinds of antiscalants, and this is a constantly changing technology. But basically, many and most antiscalants rely on phosphorus groups, nitrogen and phosphorus groups in the molecules of the antiscalants. And this is, as you know, phosphorus is another eutrophication causing nutrient. And we are also limited in and regulated on the amount of phosphorus which we can send to the sea. So these are challenges that we face when we want to supply water to the area, and we're limited by our sources and limited by the nutrients. So what do we do about this? We're constantly looking for new wells with lower nitrate concentrations. Not easy in this very deserty area. Water sources are very limited. The process of looking for new wells and searching and digging them is very expensive and takes a very long time. And very often we find wells that were fine at first. If I go back, this, for example, was a well that was developed in order to meet these low concentration needs. And within really 3 years of operating it, its concentration rose because of, as I said, because of agriculture. And but we're constantly looking, we're going further north, looking for other sources or looking for sources that are far from agriculture and adding them to our water sources. The main solution in the future, in the next 4 years or so, would be to increase the amount of desalination from seawater. Seawater, as it has a low amount of nitrogen, and also what we take from the sea, we're allowed to bring back to the sea. So we will be increasing tremendously our seawater desalination, actually doubling our water production capacity. And we're also constantly in search for nitrate removal technologies from our concentrate stream. We have just, as of last year, finished a pilot of removing nitrate from concentrate by growing algae in the concentrate stream, and also looking into developing that option. And we're also constantly looking for other technologies and working with academia and with other industrial options of removing nitrogen and phosphorus. This is just to show you about the next stage of seawater desalination, which will be called SAPHA-D. It's a very big operation because we'll have to be we're already building this pipeline into the sea to draw water from deep in the sea, bring it all the way up to 4 kilometers up to our desalination plant, and as I said, doubling our water in production capacity. And that's it. Thank you very much.
Thank you very much, Sharon, for sharing your insights. And to gain broader perspective, we'll be now shift to the north of Israel with Ayana Benet, Head of Agriculture Extension Service at the Ministry of Agriculture and Food Security. She will be speaking about the challenges faced in the Galil region, where aquaculture is a main part of the essential part of rural livelihood. Ayana, the stage is yours.
I will tell you a little bit about the relatively new regulation of inland aquaculture effluent management that is actually already applied in about 85% of the edible fish producers in the north part of Israel. We're talking about a relatively small sector of edible fish that only 2 of the farms, we're talking about about 25 farms. 2 of them are under the regulation of prevention of sea pollution that are located along the shore, the western shore, Magan Michael and the Mifrat, that are activating under the regulations of sea pollution prevention unit in the Ministry of Environmental Protection. And all of the others are actually under the regulation of effluent management. We're talking about total of 54 million cubic meters that are bought each year, okay? New water that are used in this inland aquaculture, of which like 10 it's about 15% of this amount of water is going to irrigation. Only another 15% of this amount is released to the environment, and all of the rest, it's about more than 65% of this amount of water is it's going to irrigation and trickling. So we are talking about more or less 10 million cubic meters that are released each year to the environment, and this environment is the rivers. So all of these new regulations are the purpose of this regulation is to protect the rivers and the drainage basins in the north, and these rivers are at least part of the year are active. So there's water running there. And
now we still see the first slide. So if you're switching slides,
this is the first one that I'm just showing you. I know it's in Hebrew, but the challenge is I think the basic challenge in this in applying this regulation is one of these 3 demands. This is basic demands of this regulation. One is very basic, that the water quality will stand in maximum thresholds of water quality levels that Uri was talking about, BOD, COD, a little bit more strict than the regulation of the sea pollution prevention regulation. But because of the flow rate characterization of the different rivers, the other demand that is unique to this kind of regulation is that the effluent will release under a certain demands only 3 months in each year, from October to January. This is the permitted period of releasing water, if they are, of course, good enough according to the thresholds that are demanded. But this demand of only 3 months a year releasing, it actually says that the other 9 months, the water have to be somewhere. Okay, so this is an example of a farm in a Netziv. It's down the Bet Shean Valley. On the right, the Jordan River is going, and all of the effluents eventually going to the Jordan River. Now, in order to control all of the volume of the water, first of all, the regulation demands to eliminate all of these small entries to the canals around, and it permit only one location from which the effluent water will go out, only in these 3 months that are permitted. And here you can see a program to dig a retention pond, or a sedimentation pond, which have to be quite big in order to be able to also to have the enough time of sedimentation, and also the other 3 months a year, the farms have to pump the water from the sedimentation pond back to the other ponds, and to treat them, and to circulate them, and to use them. Otherwise, they cannot release them to the environment, and this is a big challenge. We're talking about a big area, big ponds, big scale. So this is from one hand, it's a challenge, because the infrastructure is very big and expensive to fix, okay, and to manage. But on the other hand, there's a lot of spontaneous processes like biofiltration and and sedimentation that we can use as tools. So in order to apply and to comply these regulations, there was a very huge program of the Ministry of Agriculture and the Ministry of Environmental Protection that supported the input of money in all the works of introduction that permitted to these processes to really happen. And I'll show you some things that was implied and adopted. Like, this is a new sedimentation pond that created from zero, which is a big project. And of course, there's a spot for monitoring the aquaculture, the water quality and all of the parameters that needed to be monitored. Also, flow rate is very important to monitor and to control, because the river or the canals that are part of this of the environment that the regulation try to protect have certain characteristics that we don't want to harm. So this is one kind of these are a lot of works to create a bigger volume that will support the very good sedimentation, which is the most the basic process that the water quality will be achieved upon. And it is successful. The results are good, but it took like almost 7 years to complete all of these works in almost 20 farms. This is another example. The works also rely on geographical characteristics like differences in the height, and also of very improved pumps and circulation systems. And there's two beneficial results of all of this investment. Beside the relatively good water quality, that it also goes out to the rivers and also go back to circulate inside the fish ponds. But there's a very good improvement of water use. The usage of water declined in the last 3 years. We monitor it and we see it, and also there's improvement of energy efficiency because of these modern pumping and circulating systems that was adopted. I think this is it.
Thank you, Ayana. Now we turn to Dr. Amit Savaya, Project Manager in Mariculture Division at the Ministry of Agriculture and Food Security. He will present the policy and regulatory lens, highlighting how effluent management connects to national food security goals and regulatory frameworks. Amit, please go ahead.
Hi, everyone. Thank you, Ronnie. I will talk very quickly about the angle of the National Food Security Program of aquaculture. As for today, less than 10% of the fish we consume in Israel is being produced in Israel. More than 90% is imported. And in the past 12 months, we've been working on a strategic plan for the first time that will look for aquaculture, for the aquaculture sector. It means both aquaculture and mariculture. And we want to increase the percentage of fish that we produce in Israel. We are aware that it is impossible to produce 100% of the fish that we consume because the population is growing and the demand for fish is growing, and we don't have the capacity to produce everything we consume. However, we can grow to much higher percentages than the 8-9% that we are producing these days. In order to do so, we recognize the need for appropriate regulation, I would say. So as Ayana just spoke before me, the government has already understood in the last decade that something needs to be changed in this sector, because the traditional aquaculture sector in Israel was established about 80 years ago. And the environmental conditions have been changing, and people are more aware of the need to protect the environment, and this is crucial for this sector. So, as small as Israel can be, we still have a very diverse aquatic environments. And if we're talking about the northern part, where Ayana just spoke about the Valley of Springs, which is the majority of the aquaculture sector is being produced there. So we're talking about almost only freshwater systems that are mostly connected to the Jordan River. So the regulations over there should be very specific to this area. But if we're talking about aquaculture sectors on the Mediterranean coast, we also have fish farmers that are growing fish along the coast. So the regulation over there is a bit different. It should be it should consider the effluent that is being discharged to the sea. And if we are talking about Eilat region, following what Sharon Zmora from Mekorot talked about, and the Eilat region of the inland agriculture sector that needs this water. So this is a completely different environment. So I'm trying to say that the regulation on the effluent from aquaculture sectors in Israel is a complex issue. And we need to have multiple solutions for multiple situations. In Eilat, in the Red Sea, we don't want to discharge a lot of nitrate, because we are afraid that the algae that will bloom in the Red Sea would harm the corals. However, the Jordan River is a completely different ecosystem. So we are trying to tackle all of these, all of the above, all together. And we have some funds to finance work that is being done mostly in the southern region as for today, because there was a governmental resolution about this, the promotion of Eilat Eilot as an aquaculture area of Israel. So just for an example, so we are supporting initiatives that are tackling this issue of effluent, both in Eilat, where we're trying to grow fish and to treat the nitrate that is coming out of their system, so we can decrease the effluent of nitrate to the sea. And we have similar projects in the middle of the desert, where they are also working on producing fish, barramundi fish in the middle of the desert, where the effluent water is going to irrigate olive plants. And we are also supporting initiatives in the northern part of Israel, where they are trying to grow a salmon in a recirculated system. So it's, as I said before, it is a very diverse and interesting situation that we need to face, and to find that like a tailor-made solutions for every situation. So if any of you have any specific questions about it later on in the Q&A session, I would be happy to answer whatever I can. And I think that the most interesting thing for us as a government, which is always a few steps behind the market and behind the startups and the researchers that are tackling, is to find new solutions. And we have contact with a lot of companies that are promoting new ideas, and sometimes not even new ideas, sometimes just to take a technology from the wastewater area and to adapt it to the aquaculture sector. We are also doing this. So I'm calling to whoever of you that has an idea that thinks that could help both in fresh brackish, salt water, whatever. We need everything. And I'll be happy to be in contact with whoever wants to help us tackle this problem. Thank you very much.
Thank you, Amit. We will now hear from an innovative company working on practical solution. Gabi Wilkinson, CEO, and Dr. Ofir Menashe, CTO of BioCastle Water Technologies, will present how their technology addresses effluent challenges and turns them into opportunities. Gabi and Ofir, go ahead.
Okay, thank you very much. I'm going to start first to talk a little bit before I put up the presentation, because I want to show you what we're talking about. Many of you already know us from previous presentations or from personal meetings. I'm here to present the SBP capsule. This is what we call a small bioreactor platform. It's probably the smallest bioreactor you've seen, and I'm going to show you how it works and why it can be so helpful. I'm reminding you that this is a biological technology. It treats biological contaminants, which means that when we talk about ammonia and nitrates, then we're in the right place. What we do is we have bacteria implemented inside the capsule, and the capsule is put into the water. This way we have a method of bioaugmentation. Now, why would we want to do that? Because it allows us elements of control that you don't have in ordinary biological treatments. And there we go. So I'm not going to talk about the biological challenges. We talked about that enough here. And this is the enlarged capsule. The capsule has very small pores, which don't allow the bacteria inside the capsule to leave and don't allow the bacteria from the outside to get into the capsule. The water with the contaminants will penetrate the capsule and be treated inside. The elements of control that I talked about before means that we can choose what bacteria we want to use. We can choose the amount of bacteria we need, and we can choose the location of the bacteria. Soon you'll understand why that is so dominant. Aquaculture. We've used the capsules to grow several types of species. So we've grown sea bream from very small fingerlings all the way to market size in this small system that you can see on the left side. And we've grown them to market size, and without even purging, they had wonderful tastes. What's special about this system is that the bioreactor, which were the capsules, were actually inside the fish tank. So we saved all that space and all the trafficking of the water. As I said before, we're not trafficking water through the capsules, okay? The water with the contaminants will go into the capsule. That's very important. I'm going to go back to that in a moment. When we talk about salmon, right now, we have a salmon, very, very small salmon production, but we're already growing salmon. They're around 0.5 kilo to 1 kilo, and at 35 kilos per cubic meter. In the salmon production, we're doing the nitrification, which means that we have to change the water. About 30% of the water is being changed daily. But in the sea bream that we grew, 95% of the water we saved, we only exchanged 5%, which means that we had to go through a denitrification process, which we also did with our capsules. We have specific capsules for the nitrification and others for the denitrification. So when we look at our proposition value, you understand that by using the capsules, we can reduce infrastructure. You have to understand, especially in aquaculture, when we talk about the bioreactor, most of your bioreactor is not even nitrifiers. The bioreactor is full of bacteria of all kinds, and only a very small percent are nitrifiers, which means that you're feeding with oxygen, you're feeding the bacteria instead of your fish, which means that you have a lot of you're open for biosecurity can be hit. You don't have to, when we use the capsules, we're not trafficking the water through the bioreactor. So you can save energy and you can save oxygen and we can exchange the water and we're saving on space. And the flexibility allows us to build systems in the treatments that you couldn't build before. I'm going to show you a nitrification system outdoors, which will be very interesting. So what you see here is a 700,000 cubic meter pond. And in this pond, we needed to treat the ammonia coming in before they could spill the water into the river. So we have 5 cages, and within the cages, we put our capsules, and we had nitrifiers and denitrifiers. So the nitrifiers, we put in the shallow water where oxygen was high, and the denitrifiers, we put lower into the water, in deep water where oxygen was low, and we could get the denitrification process. So without building a wastewater treatment facility, we were able to treat the nitrates in the water, and in this specific system, we lowered 17.5 tons of nitrates per year. Quite fascinating. So I think we hit the spot. You're welcome to ask us questions and talk to us outside of this meeting. I think we have a lot to contribute to SeaNovation and to Eilat Eilot when it comes to treating nitrates and biological contaminants in the water and save the environment. Thank you very much.
Thank you, Gabi. Right before switching all your mics on and moving on to the Q&A session, I want to mention that today is 680 days that our hostages are still kept captive in Gaza, and we are praying for their safe return. And Eleanor, you can now switch all the mics on, and we can start with Q&A sessions. If you don't feel comfortable talking, you can write your question in the chat and we'll attend them. Any questions?
I have a question to Ayana.
I have a question. I wanted to ask if any one of you has considered, I mean, right now we're talking about treating specifically for the ones where agriculture pollutes the water. We are talking about treating that water or looking for new wells. Has anyone considered an approach whereby we reduce the initial pollution, say by smarter fertigation techniques, rather, you know? Okay, Sharon, you want me to come again? Has anyone thought of solving the problem of nitrogen pollution by helping farmers apply less fertilizer to begin with? That's my question.
Yes. In precise agriculture, which is being really promoted in Israel, there is a sector of minimizing the use of fertilizers and pesticides as well to preserve the water quality in the surrounding areas of agriculture. So it's a national aim.
Yeah. I'll just add that in the north of Israel, almost 20% of the water that fish are grown in are used again for irrigation, but it's only 20%. And also because of the sources, the source of the water are brackish. Not all of the agriculture can be utilized. Like most of the vegetables can't be irrigated in it. So it's it can't be a solution for all of the effluent.
All right, thank you very much.
Can you present yourself?
Come again?
Can you present yourself?
By video, you mean?
No, by saying who you are, where you're from.
My name is Mugendi Mudamia. I'm a founder and chairman of a group of 10 Kenyan researchers who have come together to, bridge the gap between research and implementation. So sorry for my unpreparedness. It's very hot where I'm sitting.
Good to meet you, and thank you very much for your question. Sharon, you had a question for Ayana? You can go ahead.
Yeah, she partly answered it. I was wondering really why only 20% is used for irrigation, and are you looking into ways how to increase that percentage, and why are you limited to only 3 months a year of runoff?
Okay, so I'll start with the second question. The limitation of 3 months a year is a decision of the Ministry of Environmental Protection. It's because they prefer that the effluent will be diluted in the natural flow in the rivers. And they want to preserve the habitats. So if Nahal Harod, for instance, is dry most of the year, they don't want to wet it with effluents because it's not natural. So they don't want to interfere, and not only regarding to the water quality, but also to the timing of the flows.
Okay.
So this is their designation and their decision, and this is what they are dictating. And it was a hard thing to swallow at the beginning, but there's a beneficial outcomes out of it eventually. I don't know what about the rivers. It's a different question. If it's good for the river to be wet all of the year or not, this is another question. But a lot of water are going back and recirculated in the aquaculture farms and not going out to the rivers after the application of these regulations. And there was another question about the irrigation. There's first of all, the Ministry of Health have their regulation about quality of water that goes to irrigation, and also the things of the brackish water thing that are not suitable for every kind of agriculture. And well, there's additional problems also in Israel. There's are such areas that there are changes in the agriculture that prevent of using in an efficient way this kind of water. This is basically it.
Thank you, Ayana. Any more questions? Okay, so as we close, I'd like to thank each and every one of our speakers for their valuable contribution, and all of you that joined us today. It's clear that effluent management is not just a technical challenge, but a central issue for sustainability and the growth of aquaculture in Israel and worldwide. Thank you, Elinor, and thank you, SeaNovation team. SeaNovation and AquaculTech was happy to host you here today.
Thank you, Ronnie, for hosting and moderating this wonderful webinar. I have learned a lot myself. And to all our speakers, Uri, Ayana, Sharon, Amit, and Gabi, thank you very much for taking the time for being a part of this. And I just want to reiterate what Amit Savaya ended with, is that we are looking for solutions and we are looking to solve a wide range of challenges to safeguard our future and the future of our children. There is a wonderful ecosystem happening here that SeaNovation is part of to help people to find solutions and encourage them and bring them up in the stage. So please all feel welcome to reach out to us. I will be sending you details about our demo day, which is the graduation of 5 ventures that have just finished, towards finishing a 6-month acceleration program with SeaNovation called the Wave Up. And it was directed by our wonderful team here at SeaNovation, and we would be happy for you to join and to learn of future opportunities. So thank you very much, everybody.